Hey guys, it's Chili here. For those of you who just stumbled across this video, let me give you a little bit of an explanation. So this video was actually meant to be part 2 of tutorial 1 of intermediate, and I decided to cut it out and to replan that tutorial because it was just too complicated. I'm going to talk about a lot of advanced details in this video, and I decided, they're not really necessary for you guys, and it's probably going to mess a bunch of people up. So I decided to strip it from from tutorial 1 and just release it as a bonus video. So the material in this video, you don't have to know it to follow along with the tutorial series. It's not going to be referenced in the main series. But, I mean, it's still good information, so if you're interested, by all means, watch the video, and I hope you enjoy it. Just know that the topics that I cover in here about memory allocation and about the stack frames, base pointer, that stuff is all optional at this point. Alright, let's talk about how variables are organized in memory by the compiler. So we know about the different types of variables now, but what is a variable really? Well, again, let's look at this simple operation here. Z is equal to x plus y. Now, this is how we like to think of it, but this is not how the CPU looks at the situation. From the CPU's point of view, there is no Z, X, and Y. CPUs only deal in numbers. So from the CPU's point of view, it's like, well, the integer at address, 1008 is equal to the integer at address 1000 plus the integer at the address 1004. And in fact, the way that the CPU is looking at it is even a little different than this. It doesn't look at it in terms of this whole operation. It looks at it in terms of the steps. So it would be, first load int at 1000, and maybe load it into a register called A, and load int at 1004 into register called B, and then add A to B, and then store B into integer at 1008. This is how the CPU deals with its shit. This is how we deal with this shit. We wouldn't want to have to, instead of using variable names, to use the actual numbers of the addresses. That would make our source code a hell of a lot more difficult to write, a hell of a lot more difficult to read and maintain, and it would just make for a lot of unhappy programmers. So what we do is we get the compiler to take care of that detail for us behind the scenes. We tell the compiler, okay, I want a int type variable, and I'm going to call this fucker x. And give me one x, give me one y, give me one z. And then the compiler is going to go ahead and go, okay, well, I'm going to put your x variable at address 1000. I'm going to put your y variable at address 1004, and let's put your z at address 1008. And then when you tell the compiler, do z equals x plus y, the compiler is going to look and is going to say, well, I put that at 1000, so it's going to be integer at 1000 plus the integer at 1004, and store that into integer at 1008, and then bam, 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 here's your instructions, and Bob's your uncle. And this is great now. Not only do we not have to remember all these random numbers, we can give our variables meaningful names. It's also great because we don't have to worry about arranging them in memory, making sure, none of them overlap, making sure it's an optimal arrangement. That's all handled by the compiler. Pretty fucking sweet. Now, the C++ compiler, it organizes our variables, our data storage, into 3 main classes. Those classes are called the stack, also known as automatic storage, the data segment, also known as static storage or global storage, and then the heap, which is also known as this free store or dynamic storage. And there's another special one called thread local, but we won't talk about that one here. Now, The way that looks like in memory, in the actual memory space of the CPU, is something like this. So I'm organizing this so that the low addresses starting at 0 are at the top and the high addresses are at the bottom. Now the first thing that is in memory is going to be the code. That's the actual machine instructions that are executed to execute your program. Then after that, you've got the static data, then you've got the stack, and then you have the heap, and you've got a bunch of free space after that where additional heap memory can be allocated. Now the size of the static data is fixed. It's static, it doesn't change, but the stack can grow, and it grows upwards towards low addresses, and the heap can also grow and it grows downwards. They can both also shrink, so they can grow and shrink. Now the thing about the stack is it has a pretty limited upper limit of how big it can get. Usually it's only a few megabytes, whereas heap allocation, you can have much more memory allocated on the heap, often several gigabytes of memory. Also note that this is just a general example of what a memory map might look like. It is different on different operating systems. Windows is different from Linux, is a lot different from DOS or something like that. Now let's talk about the three storage classes: static, stack, and heap. So the heap, actually, we are going to talk about this one a little bit later. We haven't used it yet. It's very important and it really deserves its own video. So for right now, just forget about the heap. It's not in our sights. And later on, I'm going to be dedicating a whole video to this motherfucker. Now, the static data, this is, in my opinion, the simplest kind of storage. And it basically works like the example I just gave you a second ago. Let me see if I can bring it up here. Yeah, like this. So what happens is you declare some kind of static variables, and the compiler will pick places in static memory and assign those addresses to the variables. Now, static variables basically exist for the entire length of the program. None are created or removed during the course of the program. That's why it's called static, and that's why the size never changes. So let's look at an example of a kind of static variable. So if you've got a class thing, it's got a couple of member variables x and y, and it's also got a static member variable s. So if you create a couple of objects of type thing, they're going to have data for x and y, but they're not going to have data for s, because s is shared by every instance of class thing. So s is stored in static storage here. This is where your s is going to be. And when you do, thing1.s, you're not accessing something in that particular instance of the class. You're accessing the static variable, which is not tied to any one particular instance of the class. It's almost like a global variable, in fact. Actually, even if you had no existing instances of this class, you can still do thing and s, and you can access this one because it always exists. Static variables exist from the beginning of the program until the end of the program. That's one example of things that use static storage. Static member variables. Another one is global variables, but we don't deal with those because they're actually kind of cancer. I'm just kidding, but not really kidding. And actually, static member variables are really close to global variables because they're stored in the same place, right? But they're just globals dressed up in nicer clothing. But that's another can of worms altogether. So yeah, the static data is where your static member variables are stored, where your globals are stored, and also there's some other shit that's stored in there, but we won't get into that today. Now, the last storage class, and the one that's really the topic for today, is the stack. And this is the most common one that you're going to be running into, that you've run into so far. Like when you're writing a function and you go int blah, or poo my poo, you create a poo, or you create an int. This is using the stack to allocate space for these variables or objects. Now, before we get into the details of the memory stack, let's first just talk about what a stack is in general. It's a concept used a lot in computer science. And basically, it's a way of organizing your data. So for a stack, there are two main operations you can perform on the stack. One is to insert data into the stack, and that's called pushing. I'm gonna push it some more onto the stack. And another is to remove data from the stack, and that's called popping off the stack. So for example, I can push C onto the stack, and then I can push B onto the stack like this. And then maybe I want to push A onto the stack. Now, popping, you always remove the top thing from the stack. So if I pop from the stack, I have to pop A. I can't pop C from the stack. Let me just do. I can't do this. It's not possible. From the stack, you always add to the top and you always remove from the top. So when I pop from the stack, I've got to pop A. And then if I want to pop again, I'm going to pop B off the stack. And then if I wanted to, I could push A onto the stack. And then, push B onto the stack. So you've got two operations for a stack, push and pop. And the stack is going to grow up like this when you push. And when you pop off it, it is going to shrink back down. It's a very simple data structure with a simple interface, push and pop. All right, now that we have a basic idea of how a stack works, let's see how that is used to actually allocate storage for variables. So here we've got some memory. It's got high addresses on the bottom, low addresses on the top. This is in our stack. Now the CPU has a special register called the stack pointer, and that shows the last used position in memory of the stack. So we can see here that these positions in the stack are used by some other part of the program. They're not important, and the stack pointer is pointing to the last used memory. The memory after that is free, and now our stack can grow into that memory. All right, so let's go over this simple function step by step and see how the memory allocation works on the stack for these different variables. So the first thing we encounter is this statement int x is equal to 60. So the first thing we got to do is we got to create the variable x. How is that done? Well, we move the stack pointer to give some more space for our variable. And now we have space for our variable here. So this is going to be x. And we also, the compiler is going to, make a note that, okay, so this spot in memory corresponds to what the programmer calls x. And the next step is to store the value 60 into that variable. So it's going to set these bytes so that the value stored here as an integer is 60. Then the next thing is to do that, but for y. So again, we decrement the stack pointer by 4, and then we make a note, okay, this is y, and then we store the value in here, 9. The next thing we're going to do is, again, create space for the variable z. So we move the stack pointer up by 4, and we make a note that this is now z. We are not initializing it to anything, so the values of these bytes is random. It could be anything at this point. Then what we're going to do is we do z is equal to x plus y. So what that does is the CPU is basically going to it's going to look up x in its table. It's going to say, oh, that's address 16. It's going to load the 4 bytes from there. It's going to look up y. It's going to load these 4 bytes. Then it's going to add that together. And then it's going to look up z. And it's going to say, oh, that's right here. And it's going to store it in here. And the value in here is going to be a big old 69. Now, when the compiler reaches this closing brace, that is the end of this scope. So all the variables created in this scope now have to be destroyed. And that process is very simple. All you do is you move the stack pointer back down to here. You say, well, I got to destroy 3 ints. 3 times 4 is 12. So you add 12 to the stack pointer, and now all these guys are gone. And you're back to where you started. Let's take a look at another scenario for stack allocation. This time we've got a local variable int z, and we've also got an array of cars a, and there's 3 cars in the array, and they're initialized to 1, 2, 3. And that is going to look something like this situation here. And I imagine you can see how that would be. But one thing that might seem confusing to you is what is with this one here, because our car array is, 3 bytes. So 1, 2, 3, what is this thing in here? Well, if you remember before, I told you that the CPU only likes to load, for example, ints. It only wants to load them from addresses that are a multiple of 4. But if we didn't put this padding in here, all of these addresses would be 1 lower. So the int wouldn't start at 1012, it would start at 1013, and the CPU would not like that. So the compiler sticks in a padding byte in here into the stack so that everything aligns nicely when it has to load these variables. And the situation is, pretty much the same when you're creating an object on the stack as well. Basically, you just, if the object is, if the class is pub, it's going to have an int, 2 ints, and this car array. And there's got to be padding in here so everything lines up. And so in total, it's going to need 12 bytes with the padding. So it just moves the stack pointer by 12, and then it initializes the parts of the memory that it has to initialize. It's the same idea, basically. Whenever the compiler sees a variable declaration like this, it moves the stack pointer by the necessary amount, and it takes note of, the different locations in memory for the things that are going to be addressed. And when it reaches the end of a scope, it's going to move the stack pointer back to where it was at the start of that scope, basically destroying all of the things that were created during that scope. Now, all the space that the function uses for local variables, plus some extra stuff that I'll talk a little bit about later, all that stuff is together called the stack frame for the function. Now, as you know, functions can call other functions. So when we look at this in a little bit more of a big picture point of view, when we enter, let's say we call the function a, so we enter this function, it's going to create a bunch of stuff on the stack, a bunch of local variables, and so that is going to put its stack frame onto the stack. The stack is going to grow up as we use space in it to allocate memory for local member variables and other stuff. Then let's say in this function a, we call function b. Now function b is going to enter, and it's going to put its frame on the stack like this. And then function b is going to call function c, and then function c allocates its variables and puts its frame on the stack. And when function c leaves, it is going to destroy its own stack frame. It's called unwinding the stack. So then C's stack frame is going to be removed from the stack, and then when B ends and it returns, its stack frame is going to be removed from the stack. And then finally, when A leaves and returns back to whoever called it, its stack frame is going to be removed from the stack. And that's generally how allocation works on the stack. All right, let's look at another situation here. So we've got a situation where we got some functions A, B, C, D. A calls C, D calls B, B calls C. So what happens when we call function A? Well, A puts its frame on the stack, then A calls C, and then C puts its frame on the stack, and then when C returns and A returns, it unwinds the stack, okay? But what happens now when we call D? Well, when we call D, D goes on the stack, D calls B, B goes on the stack, and then B is going to call C. And so C goes on the stack like this. Now, you may not realize it right now, but this is actually a big problem for the story that I gave you just a little while back. So we're going to go a little deeper now into the meta of the stack, but don't worry if a little bit of this goes over your head. It's not a big deal. Just take in what you can. So here, oh wait, I picked the wrong thing. That's no good. Let's compare these two call stacks. So this is the case for when we call A, and this is the case for when we call D. Look at the position of C. C is at a different position depending on whether we initially called A or initially called D. So C's position on the stack frame can change depending on how it was called, the call chain. And this is a problem because remember the story that we created about how stack allocation works. The story that we created was that the compiler basically moves the stack pointer, figures out where the different variables are going to be at, and then says, okay, so A, which is the member A of P, this address is going to be 1008, and this one B is going to be 1012, and C is going to be 1016. So it assigns specific addresses to these variables, and then in the code it accesses those fixed addresses. But the problem is, as we can see here, those addresses aren't actually fixed. They depend on the order in which the functions were called. So how do we solve this? Well, it turns out that the story that I gave you wasn't a complete story. It was simplified. So in reality, this is what actually happens. So when you enter a function, the stack pointer is going to be, pointing here, and you're going to want to allocate memory for your variables. So what it does is, first of all, there's another pointer, there's another register in the CPU called the base pointer. And this tells us the base of the stack frame. So what the computer does, first of all, it just tells the base pointer, okay, point to where the stack pointer is right now. This is going to be the base of the frame for this function. Then what it does is it increments the stack pointer, allocates space for the local member variables and the objects and everything, initializes all the shit, and what it does is it doesn't go, okay, so the variable A is going to correspond to address 1008. It doesn't do that because obviously these numbers here, they can change depending on how the function was called. What it does instead is this. It says A is going to be the base pointer minus 12, B is going to be the base pointer minus 8, and C is going to be the base pointer minus 4. So it defines the variables relative to the base pointer, and by doing that, it doesn't matter where you start on the stack, your addresses are always going to be correct because they're relative to the starting point of your function on the stack. So now let's look back at the original example I gave you, assuming that Z, Y, and X are local variables. So you're going to have your stack pointer up here, you're going to have your base pointer down here, and your operations here now are going to be working on addresses relative to where the base pointer is. So the basic operation is base pointer minus 4 is equal to base pointer minus 12 plus base pointer minus 8, which, boils down to these operations here. Load from base pointer minus 12, minus 8, add them together, and then store that back into base pointer minus 4. One last thing I'll mention about the stack and about stack frames, this is mostly just for fun, but so the stack frame, like I said, it contains the local variables that were declared in the function, and it also contains some other stuff down here. But what is this stuff? Well, it's a bunch of things. Mainly, one of the things that's stored in here is the return address. So when a function is called, it has to know where it's going to return back to when it's done. That is going to be stored at the beginning of the stack frame. Other things that are going to be stored in here are, for example, the parameters, the function parameters. So like when you have a function void fart and it takes an integer n, the way that integer is passed to the function is it's put on the stack and it sits here at the beginning of the stack frame, generally right before the return address. And there's other stuff in here. Mostly the other stuff is going to be preserved registers. And these are just, you know, registers of the CPU that the CPU doesn't want the function messing around with. So it saves them at the beginning of the function, and then at the end of the function, it restores them. But yeah, there's a bunch of stuff that's at the beginning of the stack frame. It's not really that important. Just wanted to let you know about it. All right, now the last thing I want to do today for this tutorial is let's play around with the debugger and some simple code and just verify all the stuff that I taught you in this lesson. So what I've done here is I've just created an empty C++ project, added one file, source.cpp, and it's just simple int main and a couple of operations here. We create a couple variables, we assign them, we return their sum. Now let's see what this actually looks like in memory when we throw the debugger at it. So let's build it, let's run it. So here we go, we got the debugger in here. We got our variables x and y. Right now they got garbage values in them because we haven't actually assigned them yet. Now, let's see if we can find our stack frame in memory before we go any further. So if we look in the registers here, and you can just open this up by going to debug windows, you can get all these different good windows in here. So we look for EBP, which is the base pointer. So here is the address where our frame, our stack frame is at for this function. So I'm going to copy this, I'm going to go into memory, and I'm going to paste this address in here. And if I press enter, so here is our frame pointer, and or here's our stack frame, our function frame, whatever you want to fucking call it. And you can see this is where EBP is pointing to, and this is actually pointing to the old EBP from the stack frame that is before us. So you can see the numbers are very similar, 00, 19, F8, and this one is 0C. So this is the stack frame that is below us. Now if we go up here, this is where our local variables are going to be at. It's going to be above where the base pointer is pointing to, right? Now if we assign 7 to x, some of these should change. Let's try that out. And there you go. Here you got your 7. It just jammed it into memory right here. And if you look at it again, if we go here, now it's got 8. Now you can see here in that picture I gave you, the ints were beside each other. But here you can see they've got actually a lot of space between them. And I don't know why that is. It's probably has to do with the fact that this the compiler is running in debug mode. So it's putting space in between the variables, maybe so that it can verify some stuff about the stack. I'm not exactly sure, but that's the way it is. Remember, the information that I gave you in that is a general information, and the actual implementations will depend on, you know, on the compiler or on the CPU architecture, on a whole bunch of different variables. I'm just giving you general information about how these things work. The details will vary. So here we see it set these variables on the stack. It set their values to 7 and 8, and then it's going to perform the addition and it's going to return that value. Now there's another pretty goddamn cool thing we can do. Let me start the debugger again, and let's go back. Oh, let's find our variables in a different way. So we have something called the watch, and the watch will allow you to jam in numbers in here, and or it'll jam in symbols and it will evaluate the symbols for you. So for example, if I jam in X, if I can just find my home row, it's going to give me the value of X, which is negative whatever. It's the garbage value. It hasn't been initialized yet. But I can do something. Don't do that. Get rid of that. I can do something else here that's pretty fucking sweet. If I can fucking edit the... I don't want to edit. I want to get rid of this. There we go. So what I can do is I can tell it to give me the address of X. So you put ampersand for address and then you put X. And now it tells me the address of X, and in curly braces the value at that address. And so now I know the address, and for some reason it's got this. Can I copy this? Can I copy you? So let's put that address into here, and let's get rid of this garbage. So now we are at X in the memory, and if I step over this, There we go. We set x's value. So here's x. I don't know where y is. The stack, but the base pointer is going to be in here somewhere as well. Let's see. 0042FEB4. So if I look for 42FE, I can probably find the base pointer. I can't see it here. What is the 42FEDC? So I don't know. It's in here somewhere. I don't care. It doesn't really matter. That's not what I'm trying to show you. What I'm trying to show you is we can look at the machine instructions if we go to disassembly. So this shows us the machine, the assembly language, and it shows us what corresponds to what lines in our source code. So assigning 7 to the variable x, that was just move 7 into EBP minus 8, just like I told you. Local variables are defined relative to the base pointer. So this is saying move the value 7 into the memory address pointed to at by EBP minus 8. So with that logic, if I go plus 8 from here, then I've got my base pointer. So this is the base pointer then. This is where the base pointer is pointing to. So yeah, see 42FE. And this value here is the base pointer for the stack frame below us. So now y is going to be EBP minus 14. So that is, this 14 hexadecimal. So 14 hexadecimal, so this is 8. So this is 16 minus 8 plus 4 is 12. So this one should be 12 bytes above. So let me see here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I think this is where y is. Let me see if I'm right. Let's step over this code. I was right. There you go. So there's where y is. And now what it's going to do is it's going to load, this is x, so it's going to load x into the register EAX. Let's try that. 7. Now it's going to add the value, now it's going to add the thing at y to EAX. So it's going to add 8 to 7. And we get F, which is correct. That's hexadecimal, 15. And then it's going to return the value. So yeah, that's how it looks in assembly. All right, let's do one more of these for shits and giggles. So now I've got a function, and that function is going to be called from main. And I'm also declaring an array, and we'll see what that does. So we got our shit here. Let's go to the watch. It doesn't know what x is because x doesn't exist in our shit anymore. So let's go into here, and well, first of all, let me show you what happens when I put in Z. It says Z is unidentified because Z doesn't exist in this scope. So if you tell the watch, tell me what Z is, it's going to be like, I don't know what you're talking about. There is no Z here. But if we put in here, for example, ARR1, then it will tell us what is currently at that location in memory. What I want to do is I want it to give me the address of ARR0. And then I want to copy that. Yes. And let's put that in here. So let's find where our stack is at. Just get rid of this. Get rid of this, where our stack frame is at. No, don't do that. Okay, here we are. Here we are. Now our array is going to be, I guess, here, 5, 8. So it's going to start right here. So now if we initialize that, we got 1, 2, and 3 in our array. And if we initialize Q, and I'm just initializing it to a hexadecimal number, so it'll be easier to read on here. That's going to be bad food, but I fucked it up. I got it backwards, so it's going to be backwards. Anyways, so we've got Q, we've got our array. Let's look at the disassembly now. So let's go to disassembly. And so yeah, we initialize our array, and that's just moving these values into positions on the stack. And then again, moving a value into a position on the stack. Calling a function, let's see what that is. Now this function call code is actually kind of interesting here. What it's doing is, first of all, before we call fart, we have to get the value in the array at index 1. So what this is doing is this is setting up the index in EAX. And the index is going to be 4. And you might say, well, why is it 4? We wanted index 1. But remember, this is an array of integers. So in terms of bytes, the first element is going to be 4 bytes into the array. So that's why it's moving 4 into EAX. Now, I don't know why it does this shift, because it's shifting by 0. So this effectively does nothing. I'm not sure what this is for, but this sets up the index. This moves the value from the array into a register. So what we're doing is we're doing base pointer minus 10. Base pointer minus 10 gives us the beginning of our array. Then we add the index. We add 4 to it to get the first element of our array, element 1. It's the second element, but it's element 1. Then we move that into ECX. So let's do that. So now ECX, where is it? ECX contains the value of element 1, index 1 in our array. And now we're going to push that onto the stack. And that's how it passes that value to the function. It pushes it onto the stack. And then it calls the function, and calling the function will jump to where the function is. I didn't step in. Fuck me. 1 second. So yeah, we step into the function call. And now it's going to jump. This is a kind of jump table thing. Who knows what's going on here, but we'll just roll with it. And now we're in the fart function. And the first thing it does is it preserves the old base pointer. And then it moves the stack pointer into the base pointer. So now it's setting the base pointer for the new stack frame. It's setting it up. And now it's subtracting the stack pointer. It's subtracting this amount. It's basically allocating space for the stack frame for the new function. And here we're preserving registers and a whole bunch of other bullshit. And I won't worry about this. This is a lot of just debugger stuff, and that's super important. But again, here we're loading, and this is now, notice that for our member local variables, it's always BP minus something. But here we have BP plus something. And that means that we're actually now working with a parameter that was passed in. So function parameters generally have BP plus some value because they're below the base pointer in the stack. So we're loading the passed in parameter n into EAX. Then we're adding 1 to that. And then we're storing that in, this is going to be Z. And then we're moving Z into EAX. And EAX is actually how functions generally return values. They put the value in EAX, and then the caller can access it from there. So passing in values is often passed in by the stack, and returning is returned by the register. But again, this varies a lot depending on a whole bunch of different things. So that's not generally how it is done. That is just one standard way of doing it. But yeah, so now it's gonna move the return value in there. It's going to now restore all of the preserved registers. It's going to restore the base pointer here, and then it's going to return to whence it came from. And here we are. We're back to where we came from. Now the return value is in EAX. It's going to store that into Q here. And then it's going to put Q back into EAX, kind of useless, but again, we're in debug mode, so when you build it in debug, generally the compiler doesn't do any optimizations to make the machine code easier to read for humans. So now we're going to put Z into EAX so that we can return Z, and then we return from the main function. One quick thing I wanted to show you here that I forgot before, if we're in the fart function, And so here's the fart function. Here is where the stack frame is. If I step over here, yeah, so here we've just set up the local variable z. So here's our stack frame for fart. But if we look down here just a little bit, we can see, if I can find it here, where 1, 2, 3. So here is the stack frame for main. You can see it just below the stack frame for fart. And yeah, now there's a lot of just space in between here, and that is added by the compiler when it compiles in debug mode. It adds a lot of extra space in here just for reasons, just to pad things out. But when you compile in release mode, this is all squished together like I showed you in the diagram. But yeah, so you can see the relationship between the stack frames of these functions. They're, like I showed you, fart stack frame is on top of the main stack frame, which calls it. And that's it. That's how stack allocation actually works under the hood. And now I want to say one thing first of all. If this blows your mind and if you're like, I can't handle this, Chili, this is too much, I got to get out of this, you're wrecking me. Just chill out, dude, because this was just a little bit of information, a little bit of background, and it's not important. We don't ever look at this shit when we're programming in C++. The whole reason we're using C++ is so that we can avoid that bullshit. I just wanted to give you guys a little sneak peek because it might help some of you to understand those things that we're going to do with pointers later on. But if it doesn't help you, then don't worry about it. Just forget about it. If you're not interested in it, forget about it. If it's too hard for you and you're feeling discouraged, forget the fuck about it. It's not a big deal. That being said, if you are interested and you like this shit, by all means, if you found some parts of this video a little hard to understand, watch it again, let it sink in. And always you can ask me questions on the Discord or on the forum, and I will answer your specific questions about the stuff in this video. Either way, I hope you liked the video. If you did, please click the like button. It helps out a lot. And I will see you soon with some more C++.